Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 5, Lesson 1 on slope and parallel lines. Now, Unit 5, obviously we're going into a brand new unit. Unit 5 is all about coordinate geometry and learning tools that will help us in the coordinate space to prove various things about geometric figures. And in this lesson, we're going to start with two of the most important ideas in all of geometry, slope and the idea of parallel lines. So let's get right into it. All right, slope. We now move into a portion of geometry where we explore space and shapes using the tools of coordinate geometry. One of the main tools we will use is that of slope of a line or a line segment. So let's take a look at the definition of the slope of a line or a line segment. The slope of a line or segment is a measurement of how much its y-coordinate changes compared to its x-coordinate when moving from one point on the line to another point on the line. This measurement is expressed in the form of a ratio, expressed as a fraction, of the change in y to the change in x. All right, exercise number 1. Two line segments are shown below, segment AB and segment CD. Letter A, write down the coordinate points for each of the four endpoints. All right, well, I know you've been reading off coordinate points for years, but it never hurts to do this again, right? So for instance, what I'd like you to do is something like this. Well, A, right, is 2 units to the right and 4 units up. So the way that we write that down when we're writing down coordinate points is we write it as A parentheses 2 comma 4, something like that. All right, what I'd like you to do is go ahead and read off all the rest of the coordinates and write them down just right in here. All right, well, let's keep going with segment AB, right? Obviously, point B is at the coordinate point 12 comma 9, all right? So B is at 12 comma 9. Point C is going to be at 3 comma 13. And point D is going to be at 9 comma 5. All right? So throughout this unit, it's going to be extremely critical for you to both be able to read off coordinate points from a coordinate grid and for you to be able to plot points when you're given their coordinates. I know you've been doing that since 6th grade. It shouldn't be a big deal, but I just wanted to mention it. All right, now let's take a look at letter B. For each line segment, find the following graphically. Express your slopes as fractions in simplest form. All right, now remember, when we have these little triangle symbols sitting in front of our variables like x and y, those stand for the change in x, the change in y, etc., right? So let's hone in simply on segment AB, right? If I move from point A to point B, then what happens is I'm going to have a change in x that's really given by this distance. And I can literally count that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the change in x is 10. And the change in y then, I can look at this way, right? I can kind of go like this, and that's going to be 1, 2, 3, 4, 5. The change in y is 5. So their ratio, the change in y divided by the change in x, is 5/10, which then reduces down to 1/2. And again, the way that we want to always be able to interpret slopes, which you've been looking at for quite a few years now, is that for every 2 units that x increases, y increases by 1 unit. All right? We're always thinking about what y is doing in comparison to a change in x. Now, CD, that's a little bit trickier, okay? And in fact, let me go over and change into red now just so that we can kind of have a nicer contrast there. Now again, I'm going to be traveling from C to point D, okay? So in that case, what's going to happen is I'm going to go like this, all right? 1, 2, 3, 4, 5, 6, so the change in x is 6, and the change in y now, 1, 2, 3, 4, 5, 6, 7, 8 is negative 8, right? Not 8, but negative 8 because literally y is decreasing. So when I go from A to B, right, both my x increases because I'm going from left to right, and my y increases because I'm going from lower to higher. But when I go from C to D, I'm going to go 6 units to the right, but then I'm going to go 8 units down. My slope, right, which is now the ratio of the change in y over the change in x, can be expressed as the fraction -4/3. And again, I want to interpret that as for every 3 units I move to the right in x, I move down 4 units in y. All right, so slope. Now, we don't want to have to keep counting in order to do these changes in x and changes in y. So let's take a look at letter C. How could the change in x and the change in y be calculated from the coordinates of the endpoints instead of found graphically? Illustrate. So this is a very inefficient way of doing it, right? Plotting points and having to count is horrible because one, right, what if, the points are spread out by a lot, right? Two, what if the coordinate points involve decimals, fractions, things like that? It's not going to be great, okay? So how do we calculate, right? Let's just take a look at AB and BC, or sorry, the segment AB. How can we calculate the change in x and the change in y simply by looking at the coordinates? Pause the video now and see if you can either figure it out or remember it from previous courses like your 8th grade and 9th grade math courses. Well, we can simply subtract, right? And that is a really important idea. The idea or the connection between subtraction and distance, right? So in other words, if I'm moving from A to B and I want to know how much x has changed, I can just do 12 minus 2 and I'll get 10. And if I want to figure out how much y has changed, I can just do 9 minus 4 and I'll get 5. And that works just as well with CD, right? Because for my change in x, I can do 9 minus 3 and get 6. And for my change in y, I can do 5 minus 13 and I'll get -8, right? So we can simply subtract. Whoops, subtract. And for instance, right, if I look at AB, where I have A at 2, 4, and B at 12, 9, right? The change in x can be calculated as 12 minus 2, which is 10. And the change in y can just be calculated as 9 minus 4, which is 5. Now, the real key when you have the change in x and the change in y, because subtraction is relatively easy, is you can subtract in either direction, you just have to be consistent. In other words, you have to either do b minus a, or you have to do a minus b, but you can't do 12 minus 2 and then 4 minus 9, right? It's got to be this one minus this one minus this one. It can't be mix and match, all right? And that can be tricky for students because the tendency is to always want to subtract the smaller number from the larger number, but you can't do that. And of course, we'll see that repeatedly as we go through these. All right, so this gives rise to the most famous formula, maybe not the most famous formula, one of the most famous formulas in math, the slope formula, right? Let's take a look at it, the slope formula. If a line passes through the 2 points x1, y1 and x2, y2, then its slope can be calculated as slope equals m. Think about it as m for movement, equals the change in y divided by the change in x, which is y2 minus y1 divided by x2 minus x1, or y1 minus y2 divided by x1 minus x2. So again, let's talk about this a little bit, right? The order of the subtraction, right? y2 minus y1 divided by x2 minus x1, or y1 minus y2 divided by x1 minus x2. And you might think to yourself, wouldn't those give you different answers? Well, they won't. They'll always give you the same answer, all right? Because the slope of a line is the slope of the line. And it doesn't matter which point comes first and which point comes second. So let's take a look at exercise number 2 and use the slope formula to calculate some slopes. Exercise 2. Use the slope formula above to calculate the slope of a line segment with endpoints given below. Express your slope in simplest form, fraction or whole number. All right, so for me, right, I will always do the following, all right? Delta x, I'm going to always list this as x1, y1, and x2, y2, and I like to do x2 minus x1. So I'm going to do 8 minus negative 2, which is 8 plus 2, and that's 10. All right, my change in y is going to be then 10 minus 4, which is 6. So my slope is going to be 6/10, which reduces down to 3/5. All right, again, interpreting this, right, for every 5 units that x gets larger, y goes down 3 units. Now, just for a moment, let's say I did it the other way. Okay, I'm going to only do it this one time. But if I had subtracted in the other way, I would have a change of x of negative 2 minus 8, which would be negative 10. I'd have a change of y as 4 minus 10, which would be negative 6. I'm going to erase this eventually. Actually, I'm going to just extend the page. My slope then, which is the change in y over the change in x, would be negative 6 divided by negative 10. But as we know, right, a negative divided by a negative is a positive, so those literally just cancel, and I would end up with 3/5 again. All right? So really, the order in which you do the subtraction does not matter. All right? So let's take a look at the next two problems. All right. What I'd like you to do is pause the video now and see if you can come up with the slope of segment CD and the slope of segment EF. Pause the video now. And I guess I maybe shouldn't say segment CD and segment EF. I'm just looking for the slope of a line that passes through these 2 points and passes through these. Now, there's certainly the case, and I'll do this often, where you don't actually have to write out delta x is this, delta y is this, and then the slope is this. So for instance, right, for CD, I might just immediately go like this. M is equal to negative 9 minus 3, right? This y minus this y, divided by this x minus this x. And I have to be very careful with my negatives and positives here. Negative 9 minus 3 is negative 12, and 11 minus negative 10 is positive 21. Now, I can reduce that because I can divide both 12 and 21 by 3, so I'll get a slope of negative 4/7. Right? And most of the time, when I do a slope calculation, I will lay it out like this. You can take it kind of more slowly, like this, that's fine, okay? But ultimately speaking, right, I'm going to be doing it most of the time like this. Okay, let's take a look at the line that passes through E and F, right? In this case, I'm going to do 3 minus 11 divided by negative 2 minus 2. Whoops, that was kind of cool. And still. 3 minus 11 is negative 8. Negative 2 minus 2 is negative 4. And negative 8 divided by negative 4 is positive 2. Now I know that we like to think about slopes as fractions. So if you left that as 2 over 1 or 2 divided by 1, that would be okay as well. That can be particularly helpful when you're trying to graph lines, which we're going to do a couple lessons from now. All right. Actually, we'll even do a little bit of that in the following couple lessons. But for right now, I'm just going to call that a slope of 2. All right, let's keep going. Now, slope is amazingly important when we talk about parallel lines. The slope of a line gives us its direction or motion in a certain sense, right? Because it's telling us how much the y-coordinate will change for a given amount of change in the x-coordinate. Due to this, we can see a simple and yet important relationship between the slopes of parallel lines or parallel line segments. So let's explore that in exercise number 3. Now this is a relationship that you have likely seen before, all right? And it's a real easy relationship, but we want to make sure we have it down. Exercise number 3. Two parallel lines, M and N, are shown graphed below. What is the vertical distance between the two lines for any points that share the same x-coordinate? Illustrate. All right, and here's what I mean. If I kind of take a look at these lines. Now I've marked some points on the lines, but of course any given line, right, any given line is a collection of an infinite number of points. So if I were to say, look at this particular point, and I were to go vertically upward and look at this particular point, that distance is 1, 2, 3, 4, 5 units. And that's true no matter where I'm at. So this distance is 5 units, and this distance is 5 units, right? So the vertical distance between those two lines is staying the same as 5 units, right? Simple enough. And this tracks with what we know about parallel lines, right? The distance between them has to stay consistent, because if the distance between them was either growing or shrinking, then eventually they would intersect at some point. All right, let's take a look at letter B. Using the marked points, calculate the slope of each of the lines. All right, now I've written all over this thing, so it's a little bit hard to even tell what the marked points are on this thing. But for M, right, let me get that over here. For M, the two marked points are here at 3, 1. Let's mark these down. And this point at 9, 5. And for line N, the two marked points are here and here. That's at -3, 2, and at 6, 8. Okay. So let's do the slope of line M together, then we'll have you do the slope of line N on your own. Simple enough, right? So the slope of line M is going to be 5 minus 1, all divided by 9 minus 3, which is going to be 4/6. I can divide both of those by 2, and that'll give me a slope of 2/3. For every 3 units that I move to the right, I move 2 units up on this line. Go ahead and pause the video and you come up with the slope for line N. Again, I have to be very careful with my subtraction here. Right here, the slope is going to be 8 minus 2, all divided by 6 minus -3. That looks like a multiply symbol. I don't want that. 8 minus 2 is 6. And 6 minus -3 is +9. So my slope is 6/9, but I can divide both of those by 3, and I get a slope of 2/3. Right? So there it is, right? I've got these two parallel lines, and what's true about their slopes? Their slopes are equal. Now, let's make sure that we kind of get a sense for why that makes sense. Let's take a look at letter C. Why does it make sense that parallel lines must have slopes that are equal? Consider what would happen if they were not equal to the distance between the two lines. So pause the video now and see if you can figure that out. All right, well, keep in mind, right, slope is how much the y-coordinate would change for a given change in the x-coordinate. And just for a moment, right, if two lines didn't have the same slope, then their y-coordinates would be changing at different rates for the same amount of change in the x variable, right? They would change by a different amount, and that would then mean that the vertical distance between the two lines would change, right? So in this case, right, if we think about it, right, every time we go over 3 units on this line, the y value increases by 2. And if I'm on this line and I go over 3 values in x, I go up again another 2. Right? So I would keep going over 3 up 2, over 3 up 2, over 3 up 2. If those didn't have the same slope, what would happen is that that vertical distance of 5 units would change, right? It would be getting smaller or larger, okay? And eventually the two lines would intersect, okay? So if the slopes are not the same, the vertical distance between the lines always takes a lot of time, between the lines would change and they would eventually intersect. Because eventually that vertical distance would shrink down to 0, and then the two lines would hit each other. All right? So literally the slopes being equal kind of create that constant separation between the two lines, never getting larger, never getting smaller, and therefore never intersecting. Okay, now let's use some slope, right? So slope and parallel lines. Let's talk about this really quick. Two non-vertical lines that are parallel will have equal slopes, and two non-vertical lines that have equal slopes will be parallel. Now, you might be wondering why I keep throwing in the non-vertical lines. I mean, it would read a lot nicer if it was just two lines that are parallel will have equal slopes, and two lines that have equal slopes will be parallel, right? But there's something a little bit funky about vertical lines that we'll talk about a few lessons from now, so we gotta kind of throw that little piece in. For now, just basically know this. Equal slopes and parallelism basically go hand in hand. If lines are parallel, they have the same slope, and if two lines have the same slope, they have to be parallel. Let's take a look at exercise number 4. Given the points A, -2, 1, B, 6, 7, C, -4, -3, and D, 8, 6, answer the following questions about segments that would connect these various points. Letter A, is segment AB parallel to segment CD? Justify. All right, well, if we're asked whether or not two lines or two segments are parallel, it basically is boiling down to one issue. Do they have the same slope? So let's go through letter A. All right, and what I like to do is I like to be pretty good about my work here. I'm going to write down AB with a little colon. I'm not going to write down AB equals. Don't do that, right? If you say AB equals, then you're talking about the length of AB. So AB colon, well, then it could be anything, right? So its slope is going to be 7 minus 1, there's my change in y, divided by 6 minus -2, be careful there. 7 minus 1 is 6, 6 minus -2 is positive 8, and we should always simplify our slopes, that's going to be 3/4. Now for CD, let's take a look at that. M is going to be 6 minus -3, that's my change in y, divided by 8 minus -4. 6 minus -3 is 9, 8 minus -4 is 12, and when I reduce, that's 3/4, and so the answer is yes. Right? Yes. They have the same slope, and therefore they're parallel. Why don't you go ahead and take a look in letter B and figure out whether segment AC is segment AC is parallel to segment BD. All right, let's do it. So for AC, now this is a little bit trickier because I have to look at this point and this point, right? I really have to hone it in. So here, my M is going to be -3 minus 1, all divided by -4 minus -2. -3 minus 1 is -4, and -4 plus +2 is going to be -2. -4 divided by -2 is +2. So the slope of AC is +2. And now, let me just change my color so that it's easier to see this. Now I want to take a look at BD. So for BD, the slope is going to be 6 minus 7, all divided by 8 minus 6. 6 minus 7 is -1. 8 minus 6 is 2. Can't reduce that at all. So when I look at those two, I can most certainly say no. They are not parallel because they don't have equal slopes. It's as simple as that. Now let's take a look at one more little problem to wrap this lesson up in a tidy little bow. Letter C. If segment ED is parallel to segment AC and point E has coordinates of 12, K, then what is the value of K? show how you arrived at your answer. All right, well, what I'd like you to do is play around with this a little bit. See what you can do, and then we'll take a look. All right, well, there's a few different ways to do this problem. I kind of like doing it in the most straightforward way as possible. The only way that ED will be parallel to AC is if they have the same slope. So the first thing I'd like to do is just remind myself, what is the slope of AC? Right, well, I calculated that before. It's right here. The slope of AC is equal to 2. So I'm just going to write down AC m equals 2, right? Now, what about ED, right? Well, what do I know about ED, right? I know that D, let me write down D's coordinates. D is at 8, 6, and E is at 12, K. All right. So let me write an expression for the slope of DE or ED just based on these 2 points, right? So based on these 2 points, right, ED will have a slope of K minus 6 all over 12 minus 8. Now, there's not a lot I can do with the numerator. I'm just going to leave that as K minus 6, but at least the denominator I can simplify to be equal to 4. All right, so whatever K is, forget about the fact that it's parallel to AC. Whatever K is, the slope of segment ED is K minus 6 divided by 4. Now, because we know that ED is parallel to AC, then we know that the slope of ED must be equal to the slope of AC, and therefore K minus 6 divided by 4 must be equal to 2. And what that now allows me to do is it allows me to solve this equation for my variable K. And let's do just a little bit of equation solving, right? This should be old hat from Algebra 1. Right, I can get rid of that denominator of 4 by multiplying both sides by 4. That'll give me K minus 6 is equal to 8. And now I can add 6 to both sides, and K must be 14. And that's it, right? That's the whole deal. All right, so let's wrap this up. We saw a couple of important things today, probably both of which were review. Number one, we talked about the slope, the concept of slope, the idea that it's a measurement of how much the y-coordinate along a line is changing for a given change in the x-coordinate. You've also known this as something called the average rate of change, okay? But we're just going to be, in geometry, calling it the slope, okay? It can be calculated by the change in y divided by the change in x, where the change in y and the change in x can both be found by simply doing some subtraction. You got to watch out for the order of the subtraction. You got to watch out for all sorts of things that get in your way in terms of subtraction, but you could also use calculators to help with that. The other very important thing we saw today was that 2 lines will be parallel if they have equal slopes, and 2 lines that have equal slopes are most certainly parallel. We'll get into the whole vertical line piece, a couple lessons down the road, but basically you want to be thinking of parallel lines and equal slopes as being sort of one and the same thing. All right, well, we're going to use this a lot, not only in this unit, but in the entire course moving forward. So make sure to get some good practice on tonight's homework on both calculating slopes and making that connection between slope and parallelism. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.